Hey everyone, welcome back. Today, we're going to tackle a principle that is, and I mean this, a total game changer in software architecture. The D in SOLID, the Dependency Inversion Principle. This is really the secret sauce that separates brittle, fragile code from systems that are truly flexible and robust. All right, let's get right into it.
But before we get to the solution, you've got to understand the problem we're trying to solve. And honestly, it's something every single one of us has run into.
I mean, you know that feeling, right? The business comes to you with what sounds like a tiny change. Hey, can we just swap out the database? And boom, suddenly the whole application is on fire. It just starts falling apart. So why? What's going on there?
Well, the bad guy in this story has a name. It's called tight coupling. Take a look here. See how our business logic, the important stuff, is basically welded directly to a specific low-level detail, like a MySQL database. So when someone says, hey, we're moving to PostgreSQL now, what do you have to do? You've got to crack open the chest of your business logic and perform open-heart surgery. It's just a mess, because that dependency is so rigid.
And yeah, this just kicks off a whole chain reaction of problems. As we just saw, changing the database means we have to change our core code. Your whole system just becomes super brittle. It feels like it's fighting you on every single change. And testing? Oh man, it's a total nightmare. You can't just unplug the real database and plug in a fake one for your tests. So what happens? Your quick little unit tests turn into these slow, clunky integration tests. It's just not good.
Okay, so how do we get out of this mess? How can we build software that actually embraces change instead of shattering into a million pieces? Well, the answer is pretty cool. We invert the dependencies.
And that brings us to the formal definition of the Dependency Inversion Principle, or DIP. Now pay close attention to the wording here because it's super important. It says our high-level stuff, like our business rules, should not depend on the low-level stuff, like the database code. Instead, and this is the key part, both of them should depend on abstractions, like an interface.
So let's just boil that down to two simple rules you can remember. Rule number one, the important high-level business logic shouldn't know anything about the nitty-gritty details. It shouldn't care how you store data or send an email. And rule number two, both sides should agree to talk to each other through a middleman, a contract. And that contract is our abstraction.
So really, the whole point of this entire exercise is to get to the exact opposite of that tight coupling mess we started with. What we want is loose coupling. That's the goal.
Okay, so that all sounds great in theory, right? But what does it actually look like when you're writing code? Let's check out how this totally transforms our system's design.
So here's the before snapshot. Our order service is just way too friendly with the MySQL database. It knows exactly what it is, it's creating it directly, it's calling all its specific methods. They're basically stuck together with super glue.
And now, look at the after. This is beautiful. The arrow, the dependency itself, has literally flipped around. It's been inverted. See, now the order service doesn't know about MySQL at all. It only knows about this generic contract, this interface, let's call it iRepository. And then the MySQL database comes along and says, hey, I promise I know how to be an iRepository. The order service is completely clueless about what database it's talking to, and the best part, it doesn't need to care.
So how does this magic actually happen? How do we connect these pieces? Well, we use a super important technique called dependency injection, or DI. Basically, instead of letting the order service build its own database connection inside itself, we build it somewhere else and just hand it over. We inject it. The class just gets the tool it needs to do its job, no questions asked.
Now, there are a few different ways to pull this off. By far the most common, and honestly the best way, is through constructor injection. You pass in the dependencies when you first create the object. It's clean, it's upfront, and it makes sure the object is always ready to go. But, you'll also see other types like setter injection or field injection, especially in some big frameworks that do a lot of magic for you.
All right, we've covered the theory, we've seen it in practice, so now it's time to see if you've really got it. Think of this as a pop quiz. These are the kinds of questions a tough professor or a sharp interviewer is definitely going to ask. You ready? Let's do it. Okay, question number one. Imagine you're inside your order service class, and you type this line of code. Database equals new MySQL database. Is that a violation of the dependency inversion principle? Yes or no?
Yes, 1,000 times yes. This is probably the single biggest red flag for a DIP violation. The second your high-level class uses that new keyword on a concrete low-level class, you've just hard-coded that dependency. You've created that tight coupling we've been talking about, and you've completely broken the principle.
All right, next up, a scenario question. So your notification service works great. It sends emails. But now product comes along and says we need to send SMS notifications too. To make it happen, you have to go back and change the original notification service code, probably adding a bunch of if-else statements. What principle are you violating here?
If you said dependency inversion, you are absolutely right. See, the root of the problem is that the service was built to depend directly on a specific email sender. It wasn't built to depend on a general idea, an abstraction, like an iNotification sender interface. If it had been designed that way, you could have just written a brand new SMS sender class and plugged it in without ever having to modify the original code. And here's a little bonus for you. This also shows how breaking DIP often leads to breaking another solid principle, the open-closed principle. They're very connected.
Okay, to make sure this idea really sticks in your head for good, I've got my all-time favorite analogy for this principle. It's super simple, it's really powerful, and I guarantee you use it every single day.
But first, let's just sear this into our memory. If you walk away with only one thing today, please let it be this quote. This right here is the absolute core of the dependency inversion principle.
Okay, here it is, the wall outlet, the power socket. Just think about it for a second. Your phone charger, that's your high-level module, right? Does it care if the power is coming from a coal plant, a nuclear reactor, or a field of solar panels? Those are the low-level modules. Of course not. All it depends on is that standard 2 or 3 prongs shape of the outlet on the wall. That outlet, that's the interface, that's the abstraction. And it's what decouples your phone from the entire power grid.
And when you start building your software using this same idea, the benefits are just massive. Your code stops breaking every time a requirement changes. The whole system becomes modular, super flexible. Unit testing suddenly becomes easy because you can just plug in a test version. It even lets different teams work at the same time. As long as you agree on the interface, the outlet, one team can build the app while another builds the database part. You're finally in control of your dependencies, not the other way around.
So I want to leave you with one final question to take with you back to your own code. Look at your classes, look at your modules, and ask yourself this. Is my code plugged into a standard outlet, or is it hardwired directly to the power plant? The answer to that question, well, it's going to tell you everything you need to know about how easy or how painful the future of that project is going to be. Thanks for tuning in.